In this short video, we talk about light guides. We can guide light from one location to another one by a set of lenses and mirrors. And the process includes partially reflection and absorption processes. It is evident that if we have more optical elements or devices, we will have more loss of power. Here we see some examples of light guides. In figure A, for example, we have used a combination of lenses. And in figure B, we have used a combination of mirrors. And the last figure shows a device like an optical fiber, which is based on total internal reflection. Optical fibers are one of the most important devices we use in science and technology. The ideal mechanism for light guide is total internal reflection without any refraction. The optical fiber includes concentric glass or plastic materials, outer cladding, and inner core, as you see in the figure. And the refractive index N2 of the cladding must be less than of the core. The light rays traveling in the core are totally reflected from the cladding if theta bar, this angle, which is the incident angle for this boundary, is greater than theta c, the critical angle. And we obtain the critical angle using the Snell's law in the previous lessons. So theta bar should be greater than sine inverse of N2 over N1. But look at these two angles, theta bar and theta. We know that if I continue this normal, I will have a right triangle, which means that theta plus theta bar is equal to 90 degrees. So the rays making an angle theta equals 90 degrees minus theta bar are confined in the core if theta is less than theta c bar. So it is clear that if theta is smaller, theta bar is greater. So the condition for confining the light in the fiber is that theta is less than theta c bar, which is 90 degrees minus theta c. Now, consider this figure. This is the incident ray, and the dashed line is the optical axis, which is the axis of the fiber as well. I have called the incident angle theta A. The refracted light into the core makes an angle theta c bar with respect to the optical axis. So if I assume that the refractive index of the air is 1, then I can write sine of theta A is N1, the refractive index of the core, times sine of theta c bar. But since theta c and theta c bar and theta c are complementary to each other, which means that theta c plus theta c bar is 90 degrees, I can write sine of theta c bar as cosine of theta c. But we obtain sine of theta c equal to N2 over N1 in the previous slide. So cosine of theta c is a square root of 1 minus N2 over N1 squared. So we can define a new quantity which is called numerical aperture, which is equal to the sine of theta A, or the acceptance angle. And using the previous relations, I can write it as n1 times cosine of theta C, which is a square root of 1 minus n2 over n1 squared, which is simplified to this, n1 squared minus n2 squared.